Hello everyone. In this video, we are going to discuss spherical mirror. Take note that a mirror is any object that will be able to produce a regular reflection, and that a reflection is the bouncing back of light as it strikes on a reflecting surface. A curved mirror or a spherical mirror is a curved mirror formed by a part of a hollow glass sphere with a reflecting surface. There are two types of spherical mirror. We have a concave mirror, which is a curved mirror with the reflecting surface on the hollow side. On the other hand, the another type of spherical mirror is the convex mirror, a curved mirror with a reflecting surface on the outer side. As you can notice, here we have the light rays coming from infinity, and it is converging on a common point, which is called as the focus. In this case, we can call concave mirror as a converging mirror. While on the convex mirror, you can notice that it scatters the light ray coming from infinity, coming from a common point, which is the focus. This scattering of light rays makes the convex mirror called as the diverging mirror. Let's try to look into the different parts of the ray diagram that we're going to have on the next video discussion. But let's focus on parts where we can analyze the light rays coming or going to our mirror. So we have the principal axis, this red, imaginary red line here. And here we have the center of curvature. We have the focal point or the focus. We have here the pole. And the distance between the focus and the pole is called as the focal length. The distance between the center of curvature and the pole is called as the radius of curvature. The principal axis is the imaginary line passing through the pole and the center of curvature. The pole is the geometric center of the curved mirror. The center of curvature is the center of the hollow glass sphere of which the mirror was previously a part. The radius of curvature is the radius of the hollow glass sphere of which the mirror was a part. The focus, it's the point on the principal axis where the light rays traveling parallel to the principal axis after reflection actually meet. And the focal length is the distance between the pole and the focus of the curved mirror. It is half of the radius of the curved mirror. There are different characteristics formed in the spherical mirror. So we have the image characteristics are as follows. We have the size of the image, the orientation of the image, and the type of image that will be formed. For the concave mirror, if the distance of an object is near, then we could come up with a bigger size of an image on a concave mirror. If the object distance is far, then the size of the image formed is smaller compared to the object. The orientation of the image formed in a concave mirror is upright if it's near and inverted if it's far. The type of image formed if the object is near is real, while if the object is far, it will turn into a virtual image. On the other hand, on a convex mirror, you will notice that the size is small, both for near and far, and the orientation is always right, and the type of image is always virtual. The uses of concave mirrors, you can use concave mirrors through the following. We have torches and searchlights, headlights of cars, vanity mirror, dentist mirror, and solar furnace. You can notice that the vanity mirror and the dentist mirror makes the object's image bigger. So you can look into the different parts of the teeth or the different uh, pores of our skin using this type of mirrors. The uses of convex mirrors are the following. We have the rear view and side mirrors for the safety of our passengers and drivers using a car or any type of vehicle. We have surveillance mirrors that we can often see in our convenience stores here in the Philippines. And we have street lamps to make the light coming from the source of the lamp scatters in the streets so that we can have a brighter streets at night. Let's move into the mirror equation. The mirror equation is a precise mathematical relationship between the distance of an object from the curved mirror, the distance of its image from the mirror, and the focal length of the mirror. You can have this equation as 1 over f is equal to 1 over dO plus 1 over di, where f is your focal length, dO is the distance of the object, and di is the distance of the image. The magnification is the ratio of the size of the image to the size of an object. This is related to the distances to the mirror. So the magnification can be calculated through magnification, m, is equal to the size of the image divided by the size of an object. Or it will be equal to minus the distance of the image divided by the distance of the object. Let's look into the sign convention. If we have a concave mirror, the kind of image we have is real and virtual. You could always say that the object is always on the positive since it's a real object. Then the distance of the image for a real object is positive for a real image. And the focal length is also positive. If we use concave mirror and we came up with a virtual image, still the distance of the object is positive. Now the distance of the image becomes negative because the image is now formed behind the mirror. Then the focal length is still positive because the focal length is before the mirror. Now, for the convex mirror, we could always have a virtual image and the distance of the object is also positive. The distance of the image is now negative since it's a virtual image and it is formed behind the mirror. And the focal length of a convex mirror is after the mirror. Therefore, the sign convention for this is negative. Let's have example for this. Example number 1. Wendy the witch is polishing her crystal ball. It is so shiny that she can see her reflection when she gazes into the ball from a distance of 15 centimeters. Letter A. What is the focal length of Wendy's crystal ball if she sees her reflection 4 centimeters behind the surface? And letter B. Is the image real or virtual? We have given in this problem the distance of the image equal to negative 4.0 centimeters. The distance of the object is equal to 15 centimeters. Let's take note that I placed negative on the distance of the image because it is formed behind the mirror. And then we are required to find the focal length. For our equation, we are going to use 1 over f is equal to 1 over dO plus 1 over di. We have our solution. 1 over f is equal to 1 over 15 centimeters plus 1 over negative 4 centimeters. We need to get the LCD or the least common denominator for 15 and 4. 1 over f is equal to 60 centimeters. P divided by 15 is 4 plus 50 divided by negative 4 is negative 15. So we have 1 over f is equal to negative 11 divided by 60 centimeters. So we now have to get the reciprocal of this. So we could have f equal to negative 60 divided by 11. So our focal length is equal to negative 5.45 centimeters. Since our focal length is negative, we could say that the image is virtual. And the distance of the image that we have is also in negative. Number 2. With his face 6 centimeters from his empty water bowl, Spot sees his reflection 12 centimeters behind the bowl and jumps back. What is the focal length of the bowl? What was surprising about Spot's reflection that have caused him to jump? We are given in this problem the distance of the object equal to 6.0 centimeters. The distance of the image is equal to negative 12.0 centimeters. Then we are required to find f and the reason why Spots jump up. Here, still, we are going to use the same equation. 1 over f is equal to 1 over dO plus 1 over di. We have 1 over f is equal to 1 over 6 plus 1 over negative 12. So the CD for this is 12. We have 2 minus 1 over 12 centimeters. So we have f is equal to 12 centimeters. Now, to identify why the dog Spot jumps up, we use the equation for magnification, where m is equal to negative di over d. Here, we have the magnification equal to minus negative 12 centimeters divided by 6 centimeters. Let's cancel out. So the magnification is equal to 2. Means that the image of Spot on the bowl bigger than his face. That's why the dog jumps off. For example number 3, a dentist uses a small mirror attached to a thin rod to examine one of your teeth. When the tooth is 1.20 centimeters in front of the mirror, the image it forms is 9.25 centimeters behind the mirror. If the focal length of the mirror and the magnification, find the focal length of the mirror and the magnification, the image. Here we have DO is equal to 1.2 centimeters. DI is negative 9.25 centimeters. And we need to find the focal length and the magnification of the two. We have 1 over F is equal to 1 over 1.20 centimeters plus 1 divided by 1 over negative 9.25 centimeters. So we have 1 over F is equal to the least common denominator is 222 centimeters. So we have 185 plus negative 24. So that 1 over F is equal to 161 divided by 222 centimeters. To get the reciprocal of this, could have 1.38 centimeters as the focal length of the densest mirror. So for M, we have negative PI is negative 9.25 centimeters. And then we have 1.20 centimeters. Units will cancel. Then the magnification is equal to 7.71. This means that the image of the two is 7.71 times bigger than the size Okay. Thank you very much for listening and for viewing. I hope you learned something about spherical mirror.